Welcome back, AP Chemistry. We have one last topic to cover for our Chapter 18 material, and that's coming back when we start to think about salts and their effects on our pH. Now, remember, when we look at our acid-base conjugate pairs, we start to see a unique kind of transition or a unique relationship between the strength of our acid and the strength of our conjugate. If you remember, we said that if you took the strength of your acid, your Ka plus your Kb, that will always equal our Kw for an acid-base conjugate pair. Essentially, what that is telling us is that if our acid is stronger, then its resulting conjugate base will be weaker, and vice versa, given that Kw is a constant. What this kind of in layman's terms means is that the stronger your acid, the weaker its conjugate, or the weaker your acid, the stronger your conjugate. And the reason this becomes important is because we have lots of different ionic compounds that have the conjugate of a weak species. I think one of the most easily recognizable and one that we should probably jump on pretty quickly is for example, sodium fluoride. Let's think about this. So let's say you took some sodium fluoride and you threw it in some water, right? You threw it into some water and it dissociates into its conjugate species or into its dissociated species. The question you got to ask yourself is, do we have the conjugate of a weak acid or base? Well, there's two things that could happen here. The first thing is our sodium could react with some waters to try to form, if we're thinking about our sodium ion here, it could try to form some sodium hydroxide, kind of our first option if we're thinking about our pairs. And then that would leave behind, what do we got, an H plus? Wait a minute. Nah, if we had a strong base and a strong acid, they're going to react and we're going to stay as just our sodium ions in water. So not a thing. The second thing that could happen is our fluoride could react with the water. This would form HF and OH minus. Ooh, wait a minute. F minus, well, that's a conjugate of a weak acid. This, in fact, will happen. And we can actually see that when we have different salts dissolved into aqueous solution. We actually can see, in this case, a increase in the pH because we've created a more alkaline or basic solution. So general rule of thumb is when you're looking at salts and you're putting them into water, look for the conjugate of a weak species, because that means your resulting solution is going to have a variation or a difference in its pH. Some more examples here when we start to think about our salts in solution. So again, just a reminder that all of our different acids and bases have different strengths. The weaker the acid, the stronger the conjugate. The stronger the acid, the weaker the conjugate, and vice versa. And so a couple examples here for us to be thinking about. If you throw something like sodium chloride into solution, right? So here's our Na plus, our Cl minus. If you throw some just regular old salt into water, we don't have any measurable change to the pH. That's because sodium, well, that would try to form sodium hydroxide and H plus, not going to happen. We just saw that. Chloride, the Cl minus, would react with the water to form hydrochloric acid and OH minus, also not going to happen. Both of those species are strong. They react strongly back and leave us as just the chloride and the waters floating around. But there are conjugates that will change our solution pH. We already kind of looked at our fluoride ion. All of these negative ions prefer to pick up H's from the water to form our hydroxides, making our resulting solution more basic, more alkaline, or higher on the pH scale. And all of these will do this. And this makes sense when you're looking at your charges. We got some pretty large charges on some of our polyatomic anions. We know a lot of these to form weak acids. And remember, if it's a weak acid, that means it has a strong bond. It wants to stay locked in that bond. And so this is why we see this change. Here for our basic cations, we're looking at our Lewis definition. We'll look at an example here in just a second of how this starts to form. But this is kind of a hydrated aluminum ion that's kind of turned our solution slightly basic. We'll look at that. We're not going to spend a lot of time on that this year, but worth noting that that is a thing that will occur. Here we've got some that actually make us acidic. If we're thinking about how these would react in solution, because we've got extra H's when we put them into solution, they give those H's away to make a more acidic solution. And again, we've got our acid creating cations, this NH4 plus. Ooh, let's look at that one real quick. Because if we're thinking about what that's going to look like in solution, oh, my iPad went to sleep. You throw some NH4 into solution. Let's say ammonium chloride. Sure, why not? Well, we already know the chloride isn't going to change anything. But our NH4 plus could react with some water to form some NH3 and H3O plus. And this very much is a thing that happened. This is covalently bonded species, sometimes comes off as a gas, which actually drives our equilibrium further to the right. But then as a result, we have more H3O plus floating around in there. And as a result, it actually forms kind of a more acidic solution, a lower pH value. Cool. So just looking out for some of these salts. We're going to practice this a little bit here more in depth, but it's worth kind of noting and thinking about what are they going to do when they react with water. Anions that are conjugate bases of strong acids have no measurable effect on the pH. They won't change, because if they form strong acids, then they are going to prefer to react back to their original species. Alkali metals and alkaline earth cations have no measurable effect on our pH. And just kind of some general rules here when we think about our different salts and whether or not they're going to form our change in pH. Anions such as carbonate that are the conjugate bases of weak acids will raise the pH of a solution, making it more basic. CO3 2 minus, you throw that into water, it ends up gaining H's from the water, leaving hydroxides behind. Acidic cations are metal cations with 2 plus or 3 plus charges, and your ammonium ion. All metal cations can be hydrated in water, forming ions using kind of the generic formula, and this would be our hexahydrate species. As a result, this then ends up forming a different pH or a acidic solution. We'll show you how that actually happens here in just a second. Cool. This is a little tricky to think about. So all we did was we took our aluminum 3 plus and we threw it into water. And what ends up happening is our kind of negative end on our water molecule. Remember, water is polar, kind of that negative oxygen end of our water molecule crowd around the aluminum and form these coordinated covalent bonds. This is our Lewis definition of acid-base chemistry. And we form kind of this hydrated species. I'm never going to ask you to predict this. I'm just talking you through this, just that if you see this, you can understand why this happens. And this does happen for almost all of our 2 plus and 3 plus metal ions in solution. We know they form this because we can actually alter this using other ligands, and we'll talk more about that in a later unit. So as a result, because it's 3 plus is pretty highly positive, it pulls all the electrons towards itself, which ultimately ends up weakening the bonds between the hydrogens and the oxygens in the water molecule. And so what ends up happening is another water molecule comes in and actually picks off one of the hydrogens. Sorry, I'm pointing at the wrong one. Picks off one of these hydrogens from our hydrated species, making a slightly acidified solution. So that's how we actually see this happening. It's one of these kind of complex ion formations. Don't worry about this one so much. If you can just kind of general trend of if it's a 3 plus, 2 plus, we know it's going to start to acidify the water. You're going to be good as we start to look at our examples here. Cool. So let's talk through a couple of these. It's good to see some examples here and just think about what they might try to form. And so the question you could ask yourself when you're looking at your ions is, will that form a weak acid or base? So we add some water. We're always throwing these into water. Will calcium 2 plus react with our water to change into calcium hydroxide? Calcium hydroxide, that's strong, not going to want to go. Our chlorides are going to try to form hydrochloric acid. That's strong, not going to go. And so we'd say this first one is going to be neutral. We don't have any change of the pH for this first example. For a second example, if we add some water to our ammonium, we know they're going to form some ammonia and our H3O plus, so that's going to make us more acidic. But does our bromide counteract that? Well, Br minus would try to form hydrobromic. That's strong, isn't going to go. We always favor the side that's got the weaker species. And so this one would be acidic. This one would be acidic. Oh, here's one of those complex ions. We know that that's going to react with some waters to form some hydroniums. That's going to form an acidic solution. Kind of just talk through an example of that. Potassium nitrate, for just thinking about what our K can do. Sorry, let me draw for just a second. It's good to talk through this whole process. Just more examples are good. I'm gonna be messy here for just a second, but it's gonna be worth it, I think. Whoa, hey, go back. Well, go back, I say. Go back. Sorry about that. So we've got two ions. We've got a K plus and an NO3 minus. I'm looking at on this next example here. Sorry, spoilers, we just saw it, but let's talk through it here. K plus would try to react with water. The K plus would try to form KOH and H plus. Well, wait a minute. This is strong, which means it's going to favor the left hand, which keeps it as our K plus. That's not going to change anything. Our NO3 could react with the water to try to form HNO3 and OH minus when that water splits apart. HNO3 is strong, so we're going to favor the other side, which means it stays as our NO3. We're not going to end up seeing any pH change because we've formed strong species and we always react away from our strong species. And so this should be neutral. And I think I already exit to escape annotation mode. And so this one is going to stay neutral for us overall. Here we got this bicarbonate ion. Bicarbonate ion, is the conjugate of a weak, or bicarbonate ion. HCO3 is the conjugate of a weak acid. It's going to want to try to form carbonic acid. And when it does that, H's from the water get bound up with this acid, leaving behind hydroxide ions. As a result, our final solution is going to be basic in nature. There's kind of a lot to think about here. We're going to come back and review more practice problems of this, but just thinking about, am I making something weak? Then it is going to go. If it's making something strong, not going to change. It's going to try to react back to what we originally had. This is our last piece for chapter 18. We're going to be coming back, doing a bunch of example problems. We've got everything we need. Our test is still a week out. We've got lots of time to be looking at these different examples and making sure we're solid. Make sure you've got the notes and come with questions when I see you in class next time. Have a great day.